Well, thank you. So I appreciate the opportunity to tell you a little bit about my work in the Great Salt Lake. Before that, I'd like to just tell you about a few of the other things that I'm working on that Scott mentioned. So I also work on hydrologic information systems, and I'm leading a project called HydroShare for developing of an information system for sharing and collaborating around hydrologic data. Some of you have probably used the software TOWDEM for extracting watersheds from digital elevation models that comes out of some of that work. And those generally fit into the area of hydrology and geomorphology, looking at the structure of river networks, distributed hydrologic modeling. I've had a lot of questions today about the snowmelt modeling work, which I've been doing, so I gather there's interest in that. Here, and the interesting part about that is recently trying to apply that to the melting of some glaciers in the Himalayas. In my somewhat distant past, I worked on non-parametric stochastic hydrology, trying to fit probability distributions, but not making assumptions that anything's following a normal distribution, for example. And I guess there's a picture of me once when I got out into the field. And then streamflow regimes for stream ecology. The question there was to try and see whether we can actually say what climate change is going to do to streamflow regime patterns, and then how that might affect the macroinvertebrates, working with the stream ecologist. And then I'll talk about the Great Salt Lake. HydroShare is actually taking up almost all of my time at the moment, because it's a sort of big multidisciplinary university project to provide infrastructure to share hydrologic data. So I had to sort of put this slide in to plug it, and you guys can all go to that website, sign up for accounts, try it out, see if you find it useful for sharing data, moving data amongst your colleagues, perhaps your own research group, and then let us know what you think. So this is actually the landing page for some data that I put for the Great Salt Lake into sort of demo it. So now this is getting back on task. I'm going to be talking about the Great Salt Lake. First, I'll give a bit of an overview, talk about, in general, how a terminal salt lake works, talk about the water budget involved, the inflows of precipitation and stream flow. The Great Salt Lake is a terminal lake, so it's only outflows evaporation. And then we'll look at the sensitivity of the levels of the lake and the variations in volume to the changes in the forcing. And we'll find out that it's really the stream flow that dominates, but there's interesting effects due to precipitation and evaporation, especially as the area of the lake increases. That's an important component of the sort of stabilizing effect of evaporation on where the lake resides. I'll talk about the salinity in the lake and how that sort of goes up and down as the lake increases, and then how to model the fluctuations in the lake and draw a few conclusions. So that's just a picture. I was once fortunate enough to get a flight in a small plane over the lake when they were surveying. They actually fly over the lake to count the brine shrimp harvest and see how many boats, and I went along for the ride. So the Great Salt Lake and its basin is located here in northeastern Utah, 4,700 square kilometers. So I was talking to somebody today, that makes it about 9 to 10 times the size of Lake Tahoe, which I was surprised. I thought it was more of a comparable size, but it's a fair bit bigger. It's got 3 major river basins that drain into it. The Bear River, 19,000 square kilometers. The Weber, about 6,000. And then the Jordan-Provo system. This is the Provo River, goes into Utah Lake, and then it's the Jordan River going north into the Great Salt Lake. Then there's this sort of west desert area to the west that's actually mapped as quite large. This boundary is somewhat fuzzy, because if you've ever driven across I-80, comes around the south edge of the lake and heads across here to Nevada, and you'll see it's really, really, really flat. So what's up and what's down, and trying to map this boundary is a little bit of a challenge. So that's where the lake is. Why would anybody care about a dead lake? Well, it's not actually dead. There's quite a lot of things going on. In terms of economy, there's infrastructure along the shore. There's this causeway that carries the Union Pacific Railroad, and you can see there was a train going past that I took the opportunity to photograph. Those trains go pretty frequently, so it's a major part of the east-west trade. Notice the difference in the color of the lake, and that's because it's much more saline on that side. There's the brine shrimping industry. There's the mineral industry. So this is the Great Salt Lake Minerals evaporation ponds, where they basically take water out of the lake, put it in those ponds, evaporate it. One of the major products that they produce is potash, potassium sulfate, and they sell that to California as organic fertilizer. And it's organic because it's made by a completely natural process, just evaporation from a lake. So I think that's quite interesting. In terms of the ecology, it's a Western Hemisphere shorebird preserve. And then there's a lot of environmental issues. Air quality is related to, I mean, sometimes you get what they call a lake stench that comes off the lake that's speculated to be due to brine shrimp. As the lake recedes and the lake's at really low levels now, there's concerns about dust. It has a moderating effect on temperature, like all large water bodies, and there's lake effect snow, which makes it great to ski in the Salt Lake City ski resorts. Recreation on the lake, there's a bit of boating, and it's somewhat of a spectacular landscape. And I'll show right at the end some of the art that people have constructed with the lake, just to keep you. So it's not all an engineering talk. This shows a bit of the Western Hemisphere shorebird reserve ideas. So some of the duck species you get, there's over 70 aquatic species, migratory birds that come from Canada. Some spend the winter, so it's important for bird ecology. In terms of the history of the lake, it's the remnant, and that's the remnant it is right now, of, in geologic times, Lake Bonneville that extended over all of this area. And there you can see in this inset where Lake Bonneville was. It covered most of western Utah, extended into Idaho, Nevada, was over 335 meters deep. Right now, the lake is on the order of 10 to 15 meters deep. More than 15,000 years ago, it was almost the entire basin was covered in lake, and it overflowed at Red Rock Pass to the north. And at one really interesting geomorphologic date in the past, that actually overflowed and broke through, and there was a massive flood where a lot of the top water from the lake flowed out, and there's real interesting geomorphology at Red Rock Pass. Well, right now, I mean, some of the water flowed out there, but majority of it has been lost to evaporation. 300 meters of water has gone, and that's left its salt behind, which makes it a really saline water body. So this is the sort of graph of geologic time, and there's sort of question marks about some of these things as people go back. And this is work from the USGS, and I'm not going to sort of claim that I really know how they did all this this reconstruction, but you can see highs of the lake during glacial periods, and then lows during interglacial. And right now, it's sort of gone down low, it went up again, and then it's back down again. And somewhere in along here was where it broke through the Red Rock Pass. So this is the record of lake levels since the first Mormon pioneers arrived in the Salt Lake Valley. So they arrived in 1847, and the first record that you can get from the USGS is actually 1847. So And if you look at the records, it's actually got an E next to it, which means it's estimated. The stories go, and I don't know how reliable they really are, that there's reports of, oh, so-and-so's horse went into the water and it came up that high on the horse, and they've back estimated the levels of the lake. So anyway, we have levels of the lake going back to 1847, but they probably are a little bit uncertain. Anyway, then you get down to more recent times. Here in 1966, the railway causeway across the lake was constructed. There was actually a trestle bridge prior to that. The trestle bridge had maintenance issues, so they built a causeway that was filled with a few culverts to let water go through, that effectively separated the lake into a north and a south arm, and the level in them is different. So the red line represents the separate measurements of level in the north arm. And the highest level of the lake was actually recorded in 1872, and then coincidentally in 1986, it reached exactly the same level. And right now it's down at one of the record lows. The north arm is 4191, which is actually almost sort of skirting with the minimum in 1963 when the lake was at its previous low. The south arm is a bit higher. There's actually a large difference between the two because over the time since the causeway was constructed, it's filled in, it's sedimented in, so the flow through it has gotten a lot less. The culverts that were actually allowing flow through the causeway started collapsing, so the railroad filled them in with plans to construct a new bridge, but they haven't constructed the new bridge yet. And there is a breach that was constructed at the time the lake was flooding, but the lake is so low that the breach is high and dry. So there's actually no flow other than seepage through the causeway between the two arms, which is why there's quite a significant gradient right now. So this is just a picture of the railroad causeway that separates the north arm to the left and the south arm to the right, and a bit of a close-up. And this is obviously when the lake was a bit higher, and there's the bridge that allows flow between the two. So this is if you go to the various remote sensing products, just to show the dramatic change in the lake from 1986 to present. So 1986 was when it was high, and the scale of these is a little bit different because MODIS doesn't go back as far as 1986, and the images you can get from Google Earth don't go as far as 2015, at least the ones you can get for free. So here you can see in 1986 the lake was really full. This island there was just a little teeny island. Antelope Island here was really an island. You can see Antelope Island here is connected to the mainland. There's this large Farmington Bay. Bear River Bay is full of water. 2012, well, that island is now sort of assimilated into this mudflat. This area to the west here is now evaporation ponds operated by Great Salt Lake Minerals. And you move to 2015, Farmington Bay has just got this little trickle going through it here, but it's mostly dry lake bed. So Salt Lake City is off to this side here, so the immediate exposure of Salt Lake City to the lake is in Farmington Bay. So people from Salt Lake City look out, don't see lake anymore, they see dry lake bed. So how does this work? We have a closed basin lake that has inflows from stream flow. There's also precipitation on the lake. Then there's evaporation, and I like to think of evaporation expressed as a depth, that then when you multiply it by the area, you get the volume. And basically, if you're thinking of the inflows, the volumes of inflows, the volumes of evaporation, if the inflows are greater than the evaporation, the level is going to rise. If the inflows are less than the volume of evaporation, the level falls. So basically, the level adjusts to fluctuating inputs so that on average, the inflow equals evaporation times the area, because you could say a first approximation of a model for how the lake worked might be to say that I is constant and E is constant, then you could solve for the area. If I was to increase, you would then figure out the lake would get to a larger equilibrium area. So here I make the point that I includes inflows from stream and precipitation on the lake. So it's Q plus precipitation times the area, both of which are subject to climate variability. And I guess at the bottom here is we're showing that the deeper lake has a much larger area. The evaporation is generally less variable than the inflows. But it also depends on the climate, the wind, intensity of radiation, and humidity. It also, in the case of the Great Salt Lake, depends on salinity. Salt water doesn't evaporate quite as easily as fresh water due to the sort of the effect of ionization in holding water. So you can think of if you've got the lake at a certain level, you can calculate the volume. There's to a reasonable approximation, a fixed load of salt in the lake. So the salt concentration is the load divided by the volume. As the level increases, the volume increases, the load remains the same, the concentration decreases. So you get an effect that as the concentration increases, with the lake going down, evaporation decreases. So that's another stabilizing effect. So you've got the stabilizing effects of area and stabilizing effect of salinity. Now, I mean, there's a few complexities involved because this would affect, well, this assumes a single concentration throughout the lake, but there really is stratification. There's a deeper brine layer. So the salinity at the surface, that's what controls evaporation, isn't exactly the load divided by the volume, but the general tendency is still the same. As the lake gets higher, the surface salinity gets less. So that's sort of a broad understanding of how the lake works. Now I'll go through the steps of showing what we know about the quantification of the various processes and sort of put numbers on some of these things to get an understanding of which are important for which have a more dominant effect on the variability of the lake than others. So our water budget. Many of you, I guess it's the first week of classes, so some of you probably had anybody have a first hydrology class this week? Nobody. He taught a first hydrology class this week, and maybe what you taught about is water budget. So change in volume is inflows minus outflows. In the case of the Great Salt Lake, the change in volume is streamflow plus precipitation, which is the depth times the area, minus the evaporation. And I'm going to put here net withdrawals because there are actually withdrawals by the mineral industries to the evaporation ponds, and there was pumping out into the West Desert at the time the lake was high. If you look at the streamflow, or the inflow is streamflow plus groundwater, that comprises about 68% and 2% of the total inflows to the lake. Streamflow comes from the three major rivers that are gauged from multiple USGS gauges. Groundwater, that's the number. And Waddell and Barton reported it in 1980, and it's just an estimate that everybody seems to use, and the quantitative basis for it is a little bit weak. And so there's an opportunity to perhaps study how good a number that is. The area and the volume can come from the bathymetry, so it's relatively easy, even if somewhat tedious and quite a bit of work, to go around in a boat and measure using sonar to measure the depth of the lake, make a map, construct effectively an underwater digital elevation model, combine that with the exposed topography to be able to quantify, given the lake at any level, what's its area going to be and what's its volume going to be. That's a sort of a geometry type of calculation. Precipitation, all the work that I've done has used the data set PRISM from Oregon State University that actually has gone back and reconstructed from the late 1800s gridded precipitation across the whole country on a monthly basis. I guess there's now daily products, but we're using the monthly data. Then you can average that over the lake itself and over the basins. This 30% is the precipitation that's actually on the lake. Then evaporation, if you look at what's lost, the evaporation is 96% of the losses, and the withdrawals, which are a combination of the West Desert pumping and the withdrawals into evaporation ponds, is about 4%. So here are some of the numbers. So the area of the lake and its basins, and then the precipitation on each of them. So I said the precipitation on the lake was about 30% of the volume going to the lake. That's represented by about 300 millimeters. So just around a foot of precipitation directly on the lake. The precipitation over the watersheds is more, and that's because of the mountains. The precipitation out in the West Desert is slightly more. If you do an average, you get the total of about 488. Then here is the stream flows. So you've got the largest stream flow comes from the Bear River. It's about 1,300,000 acre feet. Maybe I should have just put it as 1.3 million acre feet. And this percentage here is what this is as a percentage of the total stream flow into the lake. So the Bear contributes 57%, the Weaver 15%, the Jordan Provo 22%, and there's a small little bit from Davis County down here and other parts around here that don't fit nicely into these basins, for a total of 2.2 million acre feet. Then I thought it was interesting, which I always tell my students in hydrology to look at. If I tell you that stream flow is 1.3 million acre feet, is that a big number or a small number? Who knows if it's a big number or a small number? If I tell you that the US national debt is $45 billion, and that's a number I'm making up, is that a big number or a small number? Well, we don't really know, because it's a number that we can't relate to very well. But if we take the stream flow over the Bear River and we divide it by the area, you get what I'm here calling runoff and express it in millimeters. And so if you take that volume divided by that area, there's a bunch of unit conversions involved, because we've got kilometers and acre feet, and we're ending up with millimeters, but we have to deal with those unit conversions. 84 millimeters, well, that's something that you can sort of relate to. So the amount of water that comes from the Bear River is as if it's 84 millimeters of depth. And then you can relate that back to the precipitation over the Bear River is 537 millimeters. So it's only 15% of the precipitation in the Bear River is ending up in the lake. That's telling us that in the hydrologic system of the Bear River Basin, the majority, 85%, is going up as evaporation. Some of it may be going into the ground, but the longer-term groundwater storage on a basin of that size, well, where's it going to go? It's going to eventually flow out into the streams, and you could ask yourself, well, is that long enough for it to happen? And probably not, but on an about 50-year average, you would say that the balance of that is all going to evaporation. And then you can see the same for the Weber. The runoff ratio is even smaller, 10.8%, and the Jordan-Provo, 11.2%. So that's typical of the sort of dry western part of the US, and I bet you guys find for some of the rivers in Nevada, the runoff ratios are even less. But that actually tells us that there's quite a bit more water here, and if we do things in this watershed that either increase the use of the water, this is a small remnant anyway, and it wouldn't be that hard to start using some of this water here and reduce that and reduce the stream flow into the lake. Or maybe if there's perhaps urban development that results in paved areas, you might end up increasing the runoff. So then I went through and looked at the quantification of the inputs to the lake sort of in terms of time series. And this analysis starts in 1949 because that was when there was good information from Streamflow. We've got lake levels going back to 1847, but the last stream gauge on the major rivers going to the lake went in 1949. So you can see that the black line at the top is the total inflows, and there's this big event that was in the early 1980s when the Great Salt Lake was at its high, and there was flooding around some of its edges, and that was mostly stream flow. The stream flow increased significantly. The precipitation, there was a bump upwards, but it isn't as dramatic as the stream flow. The groundwater is this blue line, and we're just holding that level. The purple is the withdrawal into mineral ponds, which was really small at the beginning, and then as mineral pond harvesting of minerals has increased, it's gone there. And this was, so in 1986, with the lake at record high levels, the state had to do something. The lake was threatening to sort of burst out, flood Salt Lake City Airport, block the highways. So they constructed, and the hydrologists didn't have a good answer for what's going to happen. So the governor had to do something. So they built a pumping pond in the West Desert, a pumping station that pumps water out of the lake into the desert to the west, effectively vastly increasing the area of the lake. And the idea being that more water would evaporate from that larger area, and you would control the level of the lake that way. It was a recirculation system, so water was pumped out there and was supposed to drain back, bring all of the salts back. The intention was not to lose too much salt. As events turned out, just at the time they got this online and they started pumping, and this is the amount of water that they pumped out, the climate turned around and we entered a dry cycle, and the lake went down largely by itself, helped a little bit by the pumping plant. And some hydrologists like to say that pumping plant was a white elephant, but I personally think that without the scientists really being able to say credibly, and nobody could credibly forecast that suddenly the climate cycle was going to turn dry, the state had to do something, and they did their best with a pumping plant. So here you can see the numbers of the pumping removed 2.5 million acre feet. There was 200,000 acre feet return from the West Desert. As it turned out, when they shut off the pumps, they made a bit of a mistake and forgot about the water in the West Desert that wasn't then going to return, and a whole bunch of water sat out there and evaporated, and the salt was deposited there, and there was an incremental reduction in salt load in the lake. So you'll see that in the salinity plots later on. So one of the things that, or the questions that's being asked is how much, what sort of influence has man had, humanity in general, the Salt Lake City area, Wasatch Front, Utah has quite a lot of agriculture, and there's a lot of irrigation. Is that reducing inflows to the lake? So if we look at, have streamflow inputs changed, you can plot the Bear River streamflow, and you see that the mean is that number that I showed before, but there's a trend of about 4.4 thousand acre-feet per year that's decreasing. It does have a statistical significance to it, although there's a lot of fluctuation. And the sort of thing that you can always do with statistics that makes it challenging is you could say, oh, well, the beginning of the century, everybody knows was a wet period. That's when the Colorado River Compact was signed, and the Colorado River happened to be quite high. And if for some reason you could exclude this data, you might not get that declining trend. Well, then somebody says, oh, but if you can exclude that, you can exclude this, and you can exclude that. And then so if you don't exclude anything, that's the trend. And you might say this is due to consumptive water use in the basin. If you look at precipitation, there doesn't appear to be any trend. So here we've got precipitation actually on the lake in the black line, and overall the basins. And if anything, there's a small increasing trend. And if you're waiting for a sort of P of 0.05, you reject that trend. This just shows the data on the bathymetry. I explained earlier about as the lake got higher, it gets larger in area. And we have to build that quantitatively into our models. So this shows each arm of the lake, the south arm and the north arm. There have been different studies on the bathymetry. And you can see that when you sort of start getting to 4,200, 4,210, this is where it breaks out into the sort of large flat area to the west, and you get large increases in area for very small increases in level, much more so on the north arm. You also have to take account of the fact of the various infrastructure that's gone in. The Magnesium Corporation put in a set of evaporation ponds that they've effectively built a dike across that separate what was a lake and is now part of their pond. So the natural rise and fall of the lake is restricted to that. So when we go through and try and interpret the changes in volume relative to the measured changes in level of the lake, we've paid attention to where in the history we were with respect to whether these evaporation ponds had been constructed and perhaps other evaporation ponds. And then there's also different studies that give slightly different results that don't cover all parts of the lake. So it's all of those annoying details one has to keep track of. The evaporation from the lake. I mentioned that as the lake gets more saline, there's something that's known as the water activity coefficient that reduces vapor pressure. So some of you might recognize this equation and say that looks like the Penman equation for calculating evaporation. It's got a gradient divided by the psychrometric constant plus the gradient, an energy term, and then it's got this same term configured the other way around, and here you've got a vapor pressure deficit term, and you'd be right. That is the Penman equation, but here it's been adjusted to account for this water activity coefficient. So rather than the saturation vapor pressure over fresh water, you then multiply that by a coefficient that depends on the salinity that really reduces the saturation vapor pressure, but then when you compare it to actual vapor pressure, changes the vapor pressure deficit term. You also have a change in the gradient of the saturation vapor pressure function, because it depends not only on temperature, but it also depends on the salinity. So with those adjustments, you can then go and, for all the days in which we have data, run the equation to calculate and take various steps in salinity, run the equation to calculate evaporation, and you get a range of data, and then if you average those, you get the red dots. So basically what you do is what you see is you get the evaporation from brine, saltwater, relative to freshwater declines as the salinity increases. So with Ibrahim Mohammed, we developed this equation, or we really, a lot of these concepts were already published in the saltwater literature, and we just brought it into studying the Great Salt Lake. So that we could then calculate the evaporation based on our climate inputs. There's also a USGS model that calculates salinity calculates the impact of salinity using effectively this red straight line that gives a salinity correction factor. So some of the results I've got are using that USGS model, so they're following that line. Other of the results we've used our approach, so there's a bit of a mixture there. And there's not a really large difference between the two. It's hard to say that one fits the data better than the other. So then we can go back and look at all of the inflows to the lake, measurements in the change in level, which gives you a change in volume, and you can calculate the evaporation from the lake each year, and that's this black line. And you can see the variability of that is relatively small. It's sort of never less than about 0.8 meters. It's never more than about 1.2 meters, and it averages about 1.07. Similarly, you can look at the climate inputs and calculate the evaporation using the Penman equation, and the north and the south arm have different salinities, so you get the different results, and they tend to track the observation. So that gives us a sense that we're getting things mostly right. At least things are more or less consistent here. What we get from mass balance seems to align reasonably well with what we're getting from wind and temperature over the lake. In this case, the salinity in each arm was approximated as concentrations load over volume, which neglected the sort of exchange through the causeway. So then we might ask ourselves a question, which input is the lake most sensitive to? So here we've got, again, our water balance equation. Change in volume is precipitation plus stream flow plus groundwater minus evaporation minus the withdrawals. And to quantify sensitivity, we wanted to say, okay, how does this quantity vary relative to the variance of the change in volume? So that was the measure that we used to define sensitivity. And the idea being, if most of the variance in volume aligned with the variance of that quantity, then that quantity was contributing most to the variability. It's not whether it contributes to the overall mass balance, it's whether it contributes to the variability of the mass balance. So here we find that stream flow dominates, so the variability in volume is largely due to variability in stream flow. Precipitation has a smaller effect. The evaporation, when you increase it as volume, actually has quite a large effect. Notice that there's a negative term there. And there has to be a balancing out. As the lake goes up, it gets bigger. There's a large evaporation. We didn't calculate the sensitivities for G. Well, this would be 0 because we've got the single number. And this is it's really dominated by that single event when they had the West Desert pumping, so it didn't seem meaningful. So then we ask the question about, so we say the variability is dominated by stream flow, but stabilized by the evaporation. How does the evaporation, expressed as a volume, depend on area, as the area increases and the salinity? Because remember I said as the volume changes, the salinity changes too. So we just looked at the evaporation volume, which is a product of the area of the lake, the salinity correction factor, and then the freshwater evaporation expressed as a depth. So you've got depth times of freshwater times, this is the saltwater evaporation times the area gives the saltwater volume. We formed similar ratios, the variance of each of the quantities, and we had to bring in normalizing quantities because the units of area are different than the units of volume. So there could be some discussion as to whether we brought in the right normalizing quantities, but we tried to bring in the right normalizing quantities, and we found out that it's really the effective area that contributes most on volume. The salinity correction factor variability is very small, and the variability of the freshwater evaporation depth is even smaller. So the bathymetry area effect is most important. So that's all been looking at the volume of the lake. What about the salinity? I've said, oh, it's a great salt lake, but salty. How much salt and what's its concentration? I do not have, and in the USGS or Utah Geological Survey database, there aren't salinity measurements going back prior to 1966. I've seen presentations that have graphs of salinity going back before that, but the database I've got just started here. So starting from 1966, which is after the causeway was closed, salinity has been measured in a number of places, and they're each labeled by their station numbers, which sort of vary throughout the lake. There's the railway causeway, the north arm is up here, the south arm is down here. What we did is we took, no matter where the salinity was measured, we just plotted it there and put a different symbol depending on where it's measured. What's interesting to see is that the north arm and the south arm separate out nicely, and it doesn't seem to matter within the sort of range of this scatter where you are in the south arm or where you are in the north arm. So that sort of says that the sort of horizontal mixing within each arm is relatively good, and you can measure salinity at one point and get a representative value of the entire lake, which actually is good because it allows us to sort of pool the data. So once you've got salinity measured, then you can calculate the load, and this shows the strategy we use to do that. On any date that salinity is measured, we know the level of the lake. Salinity is actually measured at a sequence of depths going down through the lake. So you can divide up, you can say the top measurement is representative of that volume of the lake. The next measurement down is representative of that volume of the lake. So you've got the height at which the measurements are made, the volumes involved, and calculate the salt load as the sum of the loads of each of those sort of pie slice type volumes. So then you get a result that looks something like this. So again, we see the dots are the measurements. The load in the south arm is the bottom group of points. The load in the north arm is the top group of points. And then you can add the two together. To do that, we actually had to fit a curve through each because the dates didn't line up. So you fit a spline curve through it and add it together, and you get this black line that gives you the total load of salt in the lake. And then we see, okay, now in about 1986, this is when the lake was really flooding really high. It's assumed that there was no load precipitated on the lake bed, because what happens when the lake goes low is you get salt precipitating out. So if we take this as the total load of salt in the lake and draw a line back, and this line is not exactly flat because we've added to that the small amount that comes through stream inflows as well as mineral pond operation withdrawals prior to that. You can sort of backtrack and say the load in 1966 was that many billion tons, but the difference between that and that is probably within our measurement error. Then you might say, okay, well, that's the total load that's there. This is what's dissolved. So this difference there is what's precipitated on the bed of the lake, and that's what that purple line is. Then we went through the pumping into the West Desert that ended up removing some salt. And now there seems to be a declining trend, and this is where mineral pond operations have been in effect. So there's a question is, if this declining trend is precipitate, but the lake level is also going down. So is this what people are withdrawing and it's being piled up in the evaporation ponds, or is it precipitate on the bed of the lake? And we can't really tell those two apart other than to perhaps bound it. If you make estimates of what's been withdrawn into mineral ponds, you get this red line, or you can sort of extend that down to make it sort of just nick the top of the observations, or you can say that absolutely nothing is lost and it's all precipitate, and then you sort of get this range of what the total load is that's left in the lake, and this would be the range of what's inferred to be precipitated at the lake bed. So the story of salt is a little bit complicated, but the general observation is that the total load in the lake seems to be declining after the 1990s when mineral pond withdrawals, effectively harvesting the salt, seem to pick up. So that's been all analyzing the past. What might the future for the Great Salt Lake hold? So you can come up with a predictive model. You can take inputs of precipitation, evaporation, stream flow, start from initial level, go through the volume changes, evaluate the mass balance equation for each north arm and south arm separately, and output time series of levels and volumes. So here we actually have to have exchange through the causeway. So that becomes the model, and it was actually developed by the USGS when they were doing some of the early water balance studies, and we've extended the time that we can use it over. And it validates actually remarkably well, because here we've got a model that's initialized in 1966, and there's separate observations of level in the north and the south arm. Here we were driving it with the evaporation calculated from mass balance, and you can see what the modeled levels track reasonably well. So now we might say, well, I guess you can do the same for salinity. You can model the salinities in each arm, and they seem to be tracking reasonably well. And you can model the loads. So there are the measurements of loads, and now the line is the model load in the south arm and the model load in the north arm. And the modeled total dissolved load is the sort of thin black line relative to the observations. And the dashed line is the total load, and this is the modeled salt precipitated on the lake bed. So that gives you a sense that the model validates reasonably well in terms of both lake levels and volumes. So then we wanted to say, okay, so can we use our past climate data to simulate the future? So this is a fairly standard sort of stochastic hydrology approach. And we're going to basically resample years. So this is referred to as block resampling. We're going to resample entire years from the past as representative of future years, and we're going to pick the years to resample using a k nearest neighbor approach based on the total stream flow that groups together similar years and maintains a statistical dependence. So what this shows is this is the correlation of our annual inflow to the lake, and these box plots are the correlation from the k nearest neighbor model resampling of those, and it's showing us, it's giving us the correlation of the data out to about a lag of 18, where the correlation has dropped off. So then you can initialize the lake at an observed level and run simulations. So I think there was about 100 simulations ran out 10 years, and you can look at the frequency distribution of what would the level be in 10 years. So it might go down as well below 4190, which people would regard as fairly catastrophic, or it might even go up above 4205, which would be getting towards the high levels. And that's because in this resampling, I mean, we're actually resampling from the historic climate that has the high years of the 80s. So if we assume that those years could recur, the lake could certainly go up. Notice that it actually requires quite a good number of years to reach its sort of full distribution. Here, starting in 2010, by about 2018 or 2017, it's crossed that. It's sort of stabilized at that spread. So the time constant of the lake is on the order of sort of 5 to 10 years. You can also look at questions, okay, what if stream flow to the lake were to change? If the stream flow was to increase through perhaps increased precipitation with climate change, or if it was to decrease either through decreased precipitation due to climate change perhaps, or increased consumptive water use, or perhaps increased evapotranspiration due to temperature increases, you can run it out through this stochastic hydrology approach. And so we did that, and you see that the sensitivity for a plus or minus 25% increase is about sort of 4 to 5 feet, and it's more in the downward direction than the upward direction. That tells us that when the lake's small, the sensitivity is greater. You can also evaluate the impact of sort of expansion pond alternatives. So here there were two alternatives that are being evaluated. No action means that the evaporation ponds continue as usual. Preferred alternative means there was an expansion of Great Salt Lake Minerals operations. And we were looking 10 years out, what's the impact on the levels of each of the arms of the lake, as well as concentration. And on the basis of some of these results, the company Great Salt Lake Minerals ended up changing their permit request. So I guess I have to note here, these simulations are from the original request. The permit request has since evolved, and they're changing their plans to fully expand the lake because I guess they didn't. Well, they couldn't necessarily get through the sort of environmental impact of having to deal with some of the changes that would have resulted. So that leads to a question. How am I doing on time? Okay, I better hurry up. So what would the natural level of the lake have been without human consumptive use depletions? So I showed right at the beginning, the Bear River showed a trend suggesting a possible reduction in stream flow. And if you add together the other lake to the other rivers, you get about 0.8 million acre feet, or 34% of current stream flow has perhaps been reduced. If you actually go to the Utah Division of Water Resource calculations for depletions, they say that they're that big, which is 69% of current stream flow. I think that's too big, and I'm concerned about the way these calculations are actually happening. So I've done my sort of analysis with this set of numbers, and I'm still going to have some discussions with them about how to validate that. But if we add 34% back to the observed stream flow to simulate the natural lake level, this is what you get. Say you start in 1966. Here's the model with observed inflows as the blue, the observed is the black. So the fact that those two are together is validating the model. You look at the naturalized stream flow, you get a lake that right now would be about 6 feet higher. So you might say part of the low lake level now is due to our reduction of stream flow. You might ask, well, I happen to start here. Is there sensitivity to the initial condition? So you can actually start at different levels, and I showed the sort of 10-year, the 10-year convergence. When you start with extremely far apart levels, they're still back almost together after about 20 years, and by the time you get to the full end of the period. So the point here is that the sensitivity to the initial level is lost, and interpreting what the lake, the natural level of the lake might be right now doesn't depend on where you start the simulation. Let me, because I'm short of time, skip over that part of the story and just come to the conclusion. So what we find is that there's multi-year dynamic variability with sort of 5 to 10 year adjustment in time scale. Stream flow is the most sensitive input, so declines in stream flow due to depletions, withdrawals, or climate change are a concern. The lake area is the most sensitive determinant of evaporation. There is a decline in the total salt load. And you can do integrated water and salt simulation fairly effectively for addressing questions about future management scenarios. And then the depletions appear to be responsible to some degree for the current record low lake levels, some of which you see here, and I happened to take this on one of the flights. Landing in Salt Lake City, you often get a picture to take photos of the lake, so that was one of them, and I promised somebody a bit of art. So that's a spiral jetty, which is built out into the north arm of the lake, and you can see the sort of red is the sort of natural color of the algae due to salinity. Thank you. Sorry for going so long.